All right, what was due this week? Well, you had to prepare two plots, d versus t and d versus t squared. The first plot should have a text on it saying that, hey, this does not look proportional, and maybe you did that elbow parabola, okay? So what about this week? Well, part 2 of data and graphs is going to be to check the graphs from part 1. It's going to be to create an empirical formula. It's going to be to using that, find a predicted theoretical slope and plotting a theoretical line and finding your value for g and the error analysis with error propagation and conclusions and a post-lab. This particular movie is going to focus on the empirical derivation and finishing the plot. Okay? The next movie will be about finding your value for g and how well do you know that g according to your measurement uncertainties, which we answer with error analysis and the error or uncertainty propagation. Your first plot should have displacement versus time. You've stretched out both your axes. Mine is a computer-generated plot. Yours should be done by hand. You might have an elbow parabola on there. And then there should be some text explaining that this data is not proportional. And you might even go so far as to say it looks quadratic or parabolic. Kind of looks like y equals x squared in general. Your plot of displacement versus time squared should have a best fit line, and there were two methods you could have employed. One was to find, one of those methods was to take a straight edge and maybe close one eye looking through the origin and seeing the line and then throwing the paper down and drawing the best fit line. The other method would have been to draw two lines using uncertainty extremes and then bisecting those two lines. This was talked about in the previous video. Whichever method you chose to draw your line, everyone should show the analysis of that line, the simple slope, finding rise over run, and you should have written out that slope and showed the values and that ratio. Here are my values, and there's my slope from this sample data. The line should have gone through two places where it crossed grid lines. And you simply record those data values, not real data values, but values where your best fit line crosses the grid line. And then you can show your ratio, rise, change in displacement, divided by run, change in the time squared value, which would give you a slope with units of meters per second squared. Then you should have written on your graph, d is equal to this value for my slope, meters per second squared, multiplied by t squared, plus some intercept measured in meters. I'd like you to take a minute and compare slopes between you and all your lab partners. What kind of slope did your lab partner get? What kind of intercept? We're mostly interested in the slopes, but if things are wildly different and yet you all took the same data, then you're going to have to discuss amongst yourselves where the problem lies. So finally, you should have that equation written on your graph. I wrote it here, and then I wrote it here a little bit bigger. I wasn't sure if you could see the top one. There's my equation. My particular slope is 0.188 meters per second squared times t squared, and then plus 0.030 meters. That's my entire equation for my displacement for my sample data. So we've looked over the graphs from last week. You should have those done. Now we're going to launch right into creating the formula, the equation that relates displacement and time squared in an empirical manner. What do we know at this point? Is d proportional to t? And the answer is no. What about d? Is it proportional to t squared? Yes. That is the first step of the empirical derivation, is find out the base relationship between your variables. D and t were not related directly through proportion, but d versus t squared, aha, those were proportional. Step 1 accomplished. Now this simple drawing of d versus t squared shows a straight line. There must be some slope that represents that line. This is of the form y equals mx plus b. d is proportional to t squared, we can replace the proportionality symbol with what? An equality sign and a constant of proportionality. Remember, y equals m times x. That m is the constant of proportionality, the slope. For this experiment, for right now, we're just going to call the slope k to remind us it's the constant of proportionality. I know that constant is spelled with a C, but this is more fun. So we just write displacement equals k times t squared. Now very quickly, we need to take a little bunny trail about the vertical intercept. Y equals mx plus b. In this situation, what does the vertical intercept represent? It's some initial offset. We call this the d naught. The naught just simply means the initial point, okay? Oftentimes, in this case, it's when the x value, t squared, is 0. What is the d value? It's called a systematic offset. When you make a plot with real data, you're going to have two types of errors present on the plot, naturally occurring. One of those errors is called a systematic offset, and the other one is called random scatter. The systematic offset in this example is a negative intercept. In the previous graph, it was a positive intercept. What do we mean by a systematic offset? We mean that something was done in the measurements and it was done consistently to every single measurement. So in the case right here, every measurement was mismeasured by 2 centimeters too short. In other words, someone was doing an experiment with a straight edge and they had a ruler that was cut off the last 2 centimeters, and yet they didn't know it. So they took all their measurements, and instead of measuring 10, they measured 8 centimeters. And instead of measuring 100, they measured 98. For every single measurement, they mismeasured by 2 centimeters, which would take this line and vertically shift it down, every single data point uniformly. Or if they measured too long, it would shift all the data points vertically up. We call that a systematic offset. It's something intrinsic in our measurements that was consistent. It was consistently off. A systematic offset, a shifting of the data. The other type of error is random scatter. Random scatter illustrates for us the fact that we are taking measurements and there is uncertainty in the measurements. This is not a systematic offset. This is an uncertainty that, in this case, for our experiment of d versus t squared, we had lots of uncertainties that came from timing and from placement of things, and sometimes things were long, sometimes they were short, and that is reflected in a scatter plot, where the data is scattered about a line. If all this data sat perfectly on the line, it probably wasn't real data. Okay, the scatter is represented in real data very clearly when you draw a best fit line, because the scatter shows the data sometimes above, sometimes below, sometimes very close, sometimes further away from the line. And you can see from my real data versus the line that my data points are sometimes above and below by different varying amounts. That's random scatter. So just to review what we mean by an empirical derivation, this equation that we wrote on our plots is not sufficient. We cannot take this equation and publish it to the world and say, create an incline and take your data and it's going to behave like this. We can't do that because this particular slope was for our experiment. That k value, that constant of proportionality, was very specific to us. What we'd like to do instead is have a more general formula. In other words, displacement is k t squared plus d naught. Now we're going to suppress the d naught shortly, but the question now is, what is k? What is, I don't mean decimally for your experiment, but what is k in general? In other words, what physical properties are hiding within inside of k? K is part of our experiment, and there were physical things going on affecting our experiment. What are those physical entities? Well, what do we know about K? One of the first things we can ask when it comes to finding the constant of proportionality is, what are the units? We call this dimensional analysis or unit analysis. So we take our base equation, our generalized equation, and we break it out into the units. Displacement is in meters, t squared is in seconds squared, and d naught is in meters. We need to have meter plus a meter equals a meter. But right here we have seconds squared. We don't know the units of k, so what can we do to seconds squared to yield a meter? Well, we can simply multiply by meters per second squared. If we multiply that by seconds squared, we're left with a meter. So these are the units of k, meters per second squared. Wow, that's pretty remarkable. We found the unit of k is a meter per second squared. That's the unit for acceleration. We had an acceleration in our experiment. Now, don't think too far ahead. We're going to take baby steps here, okay? We have an acceleration in our experiment, and we had the acceleration due to gravity in our experiment. So maybe k is simply the acceleration due to gravity. So this is our next educated guess for the empirical derivation. We're trying to solve what's hidden inside of k. And our first peeling back is that, oh, it could be g, the acceleration due to gravity. So let's write that out. D predicted is g t squared. We'll suppress the d naught from now on because d naught again was specific to our experiment. We want to produce this equation and publish it to the world, allowing anybody to predict displacement when they know a particular time or vice versa. So that's our new equation. D predicted is equal to g times t squared. Good or bad, we don't know yet, so let's find out. Let's draw this data on the same plot. Now, I don't want you to really do this. I'll do it up here. How many points do we need to draw a line? And yes, by the way, the data produced by d is equal to g times t squared is perfectly linear. This is not scattered data like our real data with uncertainties. This data fits on a line. So how many points are required to make a line? Last time I checked, 2 points make a line. One of those points can be the origin, because we're saying that there is no d naught, there's no vertical shift in the data. We're going to go through the origin. When there is no time, there is no displacement. So we write out our equation. My predicted displacement is 9.8 meters per second squared times t squared, and we're going to plug in 0 for seconds squared for the origin, and 0 goes here, and our product gives us 0 meters for displacement. The next point I want you to do, and yes, largest t squared from your data. So look at your data table and look at the last value for t, then it was squared. Use that squared value, the largest one, and put it through this equation. When I put my sample data through here, I have 9.8 meters per second squared times 8.53 seconds squared gives me 83.5 meters. So you should have 2 data points. One is the origin, and the other one is the time squared value for the x and the new predicted displacement for the y. Now, you're not going to make a plot with these. You're just going to make a note. I'm going to show you what my plot looks like. And you probably already know this, but we're just doing this in baby steps. We have displacement. This is my real data, and here's my prediction. You can see the slope of 0.188, about 0.2, and here my predicted slope is 9.8. These numbers are wildly different, and it's revealed on the plot. Here's my prediction. The scale goes up to 90 meters. And I'm pretty sure that our experiment did not go beyond 2 meters. 90 meters is well outside of the scope of this lab. Here, right here, it's almost a horizontal line is my real data. There's a tiny little bit of slope here, but on this scale, it looks like almost a horizontal line. So we'd have to say what? We'd have to say no. K cannot be simply g, the acceleration due to gravity. There's no way. But how can we scale k down? What can we do to k to bring it down significantly? My slope is about 0.2 meters per second squared, and this is 9.8. So it looks like one order of magnitude, almost two orders of magnitude. An order of magnitude is when we simply move the decimal place one way or the other. And it looks like we need to move the decimal place once and almost twice. In Denver, Colorado, G is 9.80 meters per second squared. Just a quick little note. At sea level, it's 9.81. See, in Denver, we're at a mile high, and Newton's law of gravitation tells us that the further away you get from the center of that large mass, that separation, when that separation between those two masses increases, your value for gravity, the acceleration due to gravity, will go down. But getting back to this question, what can we do to k to bring it down at least one order of magnitude? What can we do to scale down k? Was there something else in our experiment that was a nice scale factor? Now this is where we have to be careful. K, being g, did not work. But something did work with that relationship. What was it? The units. The dimensions of g matched the dimensions of k, meters per second squared. So is there something else in our experiment that would be a good scale factor and yet is dimensionless? Have you thought of it? What did we do in our experiment? We didn't drop the ball vertically or drop the cart vertically. That would have crashed and probably broken, and it would have been way too fast to measure. Instead, we set up an incline. Do you remember the incline and how we measured h and L? We said that the sine of theta related h to L, and by h I mean the height of the block, and L was the distance between the supports. And now we have g sine theta. This is our scale factor. Do you remember that discussion about sine theta and how at a horizontal the sine of 0 is 0 and the sine of 90 degrees is 1? The sine of theta naturally scales us from none of gravity, 0 times gravity, to 1 times gravity, and all the scale factors in between. So my sine theta just happens to be 0.0354. Yours should be something similar-ish to this. And when I do this product, I get 0.347 meters per second squared. Remember, this is my new guess for k. G times the sine of theta, and it's just our next guess. I come up with this for my data slope, 0.188 meters per second squared, and you can see these two numbers are much closer than my first guess of simply g. So I think with g sine theta we're honing in, but let's look at the plot. Have we really honed in well? We're asking the question, is g sine theta my new k? And here are my two equations written where I can see the slopes next to one another. And here's my predicted line. It's much steeper than my data, but at least I'm on the same scale now. So I think we've made progress. We have not adjusted the units of k, which was important. Sine theta was dimensionless, and it scaled that slope, which was very, very steep, way down, okay? An order of magnitude and then some. But are you satisfied? We might be satisfied at this point and just say, well, I found k is equal to g sine theta, so my predicted displacement for the whole world to see is just simply g times their sine theta, and then they can multiply by t squared and find out where the cart's going to be after a certain amount of time. This will work. But I think if we publish that, and 1 million people took this data, and we had some place for everybody to report the slope of their data, we would find something consistent over and over and over again. There'd be some randomness in this data, but in general, we might see a pattern. This separation in these two slopes, let's just take 6 sample values from students. Here are some sample data slopes, the slope from their data when they plotted d versus t squared, and we've suppressed the units, but here are the numbers for the slope. And then we take g sine theta, and here are those numbers. Do you see any kind of pattern between these two? If you look really carefully, you can see that the data from their slope is about half what g sine theta is. So if we take g sine theta and multiply it by half, look at these numbers over here. The sine theta was from their particular experiment. G was 9.8. And when we cut that product in half, we get a slope that is very, very similar to the data slope. And if we had enough data from many, many different experiments and saw that consistently my slope was 1/2 the prediction of g sine theta, it probably means that g sine theta is twice as big as it needs to be. Well, isn't that taking a lot of liberality? Isn't that kind of taking a lot of freedom with this empirical derivation? Sure. That's the whole point of an empirical derivation. We don't know the final equation. We're simply giving our best educated guess. We made our first guess with d was not proportional to t. It looked to be quadratic, but there it was. It kind of looked that way. So we plotted d versus t squared, and that appeared to be linear. Then we did our best fit line, drawing things by hand and estimating a slope. Then we made the assumption that, well, gravity's in the experiment, the right units. And then we made the assumption that the angle theta for the incline, the sine of that angle, was our scale factor. So all of these were liberal approaches. So why not just simply also cut things in half? If consistently my prediction is twice what it should be. So this becomes our new value for k. 1/2 g sine theta. After all this derivation, we have not changed the units. We're in meters per second squared. We scaled it by sine theta, h over L, and then we cut it in half, made it even smaller. All this product was based upon g, the acceleration due to gravity. So here is our new formula. This is the result of our empirical derivation. We started with a question, displacement versus time. What is the relationship? And we've ended with an equation. 1/2 g sine theta t squared will give us a predicted displacement. Now we can celebrate. I'm reminded of this story. There were some monks who were busily working on copying scripture, trying to be faithful in every character and every word. And this head monk went down deep into the recesses, into that lower temperature area where things could be preserved, and checked on the status of this one monk who'd been down there for quite some time. You see, the head monk heard through all those staircases some howling. It almost sounded as if somebody was weeping. And so he went down there and saw the monk, and there he was, just crying hysterically, out of control, unconsolable, this monk was. And the head monk looked at him and said, "What's wrong? What's wrong?" And the guy looked up from the pages and was pointing and said, "It says celebrate." Sorry. So one thing we can do with this new predicted formula, 1/2 g sine theta t squared, is write it at the bottom of page 2 of the data tables. We're describing all the columns. In the far right column on page 1 is the predicted displacement, or the theoretical distance. And we can write out this equation, 1/2 g sine theta t squared, at that location. Now we can go to our plot. We have this master equation from our empirical derivation. We can take this model and we can evaluate 2 data points. And I want you to do this, and I want you to take those 2 data points and put them on your plot and draw the line that connects those 2 data points. Remember, the first data point is the origin. The second data point, I want you to use your largest t squared value. Plug that in here, use your sine theta, use 9.8 for g, meters per second squared, and then cut it in half. When I do my sample, 1/2 9.8 times my value for sine theta, 0.0354, multiplied by my value for t squared, which was 8.53 seconds squared. I've suppressed the units here, I apologize, but my product gives me almost 1.5 meters. So draw this line using that new data point with t squared and d, and then the origin. And then write that equation on your plot. What is the value for the slope? Evaluate 1/2 g sine theta numerically and record that as your predicted slope. So here is my predicted slope, 1/2 g sine theta. You can see the best fit line, not the best fit line, but the perfect line drawn with just two data points. One is sitting at the origin and the other one was at my largest t squared. I connect the 2 points. Any other data point calculated for any value of t squared would yield a displacement that sits exactly on this line. You see, the prediction is of that nature. There is no scatter in that data. We simply have y equals m times x. So draw that line and write the new equation using your predicted slope. We should make a word real quickly about kinematics. Kinematics is the study of motion relating position, velocity, and acceleration for objects that are under constant acceleration. So if we take a mass and hook it to a spring and then pull down and let it bounce up and down, that's not constant acceleration. Kinematics would not work. But if we have a cart sitting on an incline or take a ball and drop it vertically, these are situations where the acceleration is constant. We can employ some general formulas to that motion. And this is one of those formulas. Position minus the new position is a function of time minus the initial position, that's displacement, is equal to 1/2 at squared, where a is constant, plus v naught t. V naught is the initial velocity of the system. In other words, the velocity at time equals 0. In this experiment, when we took a cart and dropped it, our timer started when the cart was motionless. So in other words, V naught was 0. This term goes away. And we'll notice from here that A is g sine theta for this experiment. So the kinematics, we see that 1/2, cutting in half the g sine theta, or the acceleration. So we've accomplished creating an empirical formula. We found the predicted theoretical slope was just g times the sine of theta times 1/2. And then we found the theoretical line. Next, and it's going to be in the next movie, we'll find a value for g for your data. And we'll compare that to the g that's accepted in our location. And then we'll take our value for g and try to put some error bars around it of, here's my value for g, but how well did I really know that value? And the way we're going to answer that question is with error propagation. What happens to those uncertainties as they propagate through all our calculations and our plots and finding slopes? So we've successfully empirically derived a formula that we can publish to the world and say, set up an incline, measure your h and L for the incline, and you can predict how far away things will be in a given amount of time. We found the constant of proportionality, or the predicted slope, to be 1/2 g times h over L. And our equation for prediction, the predicted displacement, is simply that slope, 1/2 g h over L, or 1/2 g sine theta times t squared.